Welcome to P. Clark Calc, where we do practical calculus for the busy math student. And today we're going to take a look at an application of an infinite geometric series that you may not have thought about. So here we're going to use an application of the sum of an infinite geometric series, which, if you can identify an infinite series as geometric in the form of a times r to the n minus 1, if we're starting n at 1 on our index values, or a r to the n if we're starting n equals 0, if that common ratio is less than or equal to 1, or its magnitude is anyway, then we can find the sum as a divided by 1 minus r. And you may have actually learned that formula many years ago in one of your Algebra 2 classes or something. And the example here shows a repeating decimal, which we may not think of as an infinite geometric series. So sometimes to apply the infinite geometric series formula, we need to rewrite our expressions to make it look like an infinite geometric series. And it all kind of starts with expanding out our repeating decimal. I can take 3.42 repeating and write it as 3 plus 0.42 plus 0.0042 plus 0.4042, and so on. So if we look at the term of 3 out front, we're going to separate it off of the repeating decimal, so just don't forget about it. So we have 3 there. And then we have the sum of these terms, which, as we can see, each one is the one before it multiplied by 0.01, which indicates our common ratio value here when we set up our sigma notation way of expressing this repeating decimal is going to be 0.01. So if we rewrite the expression now, we have the 3 out front, and then when we take an expanded form and we're converting it into the infinite geometric series notation, people sometimes get a little bit confused with the index values and the exponent of the common ratio. It's all relative, though. I mean, in the top version here, if we want to begin describing our series as term n equals 1, then it's going to be written as a times r to the n minus 1. Or if we want to begin with n equals 0, which maybe is not intuitive here, it would be a times r to the n. But they're equivalent. If you start plugging the terms in, writing it in expanded form, they're going to be identical. And sometimes people get a little bit confused as to what is meant by a. And a is just the first term of the series, wherever you're starting your index value. So if you don't want to play games with the indices, you can just go ahead and look at your terms and say, well, the first term then is going to be the 0.42 on my infinite series. So this is going to be a. So we're going to define this as a at 0.42 and the common ratio at 0.01, and then it's just a matter of which format we want to use. Now I think we'll use the one on the top. It's kind of intuitive to start with term number 1. So let's write this as the summation as n goes from 1 to infinity of 0.42 and then it's going to be 0.01 to the n minus 1. Because again, when you have a geometric series, the subsequent terms are all defined by taking the first term and multiplying it by the common ratio to the n minus 1. And that's what we're showing here. And if you plug in a couple of numbers, you could see it. The first term will be 0.42, the second term 0.0042, and so on. So that's the correct notation using the sigma notation for our geometric series. So now we can go ahead and apply our formula and find out that our total here is 3 from the original integer part of our repeating decimal, plus a 0.42 divided by 1 minus r, so 1 minus 0.01. So we end up with 3 plus 0.42 divided by 0.99. And if we just multiply top and bottom of that fraction by 100, our expression then is 3 plus 42 over 99. And now we can prove that repeating decimals are rational numbers. That's the one that algebra students don't often believe at first when you first tell them. But this can be written as a fraction, because then when we convert 3 into the fraction with the common denominator of 99, we have 297 over 99 plus 42 over 99, and then we get the exact value of the repeating decimal, which is going to be 339 divided by 99. And if you take a second and you want to check that with your calculator, you'll see that all checks out. And we're kind of used to it from algebra. And when you convert a repeating decimal over into a fraction, we get used to seeing these denominators of 9 or 99 if it's a 2-digit repeating block, or 999 if it's a 3-digit repeating block, or maybe it reduces, so sometimes you'll see 3 or 33 or 333 in the denominator. So that's one application of the infinite geometric series formula. Anytime you see a repeating decimal, you can use that technique to express the exact form as a fraction. At P. Clark Calc, we do practical calculus for the busy math student, but if you want to learn more about infinite geometric series or infinite series in general, you can find them on my textbooks, which are available on Amazon for a nice price. And until next time, I'm P. Clark.